Okay, so let's review the first practical that we've done, starting with oscillating masses on springs. Okay, so the first thing we need to do is measure the unstretched length of the spring, the L0 measurement. So the first thing to notice is that the unit it wants is millimeters. So having measured it, I got a length of 20 millimeters. And I'm giving that to no decimal places because a ruler that I'm using can measure to the nearest millimeter, so we shouldn't have any decimal places. Okay, so then we've hung a 300 gram mass on the spring. The new length, again in millimeters, is 140, giving us a total extension of 120 once we've subtracted the original length of 20. Again, these are quoted to no decimal places because our length was measured to the nearest millimeter, and then both of our values had no decimal places, so the calculated value should be to no decimal places. Calculate the value for the spring constant using this equation. So we've got the force, 3 newtons, and we've got an extension of 20 millimeters, giving us a spring constant of 0.025 newtons per millimeter. So with this question, lots of people didn't give a unit and hence lost the mark. And even if you don't remember what the unit of spring constant is, you can use the equation to figure out, because it's a force divided by a distance, so we should get a unit of newtons per unit of distance. Okay. So moving on, we're now going to time oscillations. So what we're going to do, pull the mass down and then release it. So you want to give it a fairly small displacement, otherwise it will be oscillating all over the place. And you probably want to give it a couple of oscillations to settle into its rhythm before you start timing. Okay, so for 300 grams, I got a time of 6.46 seconds. For 10 oscillations, giving a time of 0.046 seconds for 1 oscillation. So for the measurement of 10 complete oscillations, so I should be more specific, the reading 6.46 seconds, that should be to 2 decimal places because that's the precision we get from a stop clock. And then the time for 1 oscillation should be 3 significant figures because the 6.46 is a 3 significant figure number. The 10 is an integer, so it's technically infinite significant figures. So we're going to give our answer to 3 significant figures. Okay, so replace the 300 gram mass with 500 and repeat the steps. So again, we get a time to 2 decimal places, and this time we get a time period of to 4 significant figures because 10.21 is a 4 significant figure number. Okay. So here are our 2 times for the 2 measurements. So a student suggests that the time taken for 1 oscillation should not be affected by the change in mass. State whether your results support the suggestion. Justify your answer by reference to your results. So we can't answer this question without considering the error, or the uncertainty, I should say, in our readings. When we're timing things with a stop clock, most humans have an uncertainty of plus or minus 0.02 seconds. Some might be slightly less than that, but that's a conservative value for our timing uncertainty. So if we get a time of 5.23, the actual time that we were trying to measure could have been 5.21 or 5.25, or anywhere in between those values. So if we're going to say there's been a significant change in time, we need to consider this uncertainty. Okay, so if we go back to the question now, so the difference between the times from 500 grams to 300 grams is 0.375 seconds. Okay, so those are the time difference. So our uncertainty in the measurement for 10 time periods is 0.02 seconds. So we can clearly see that the supports do not support that suggestion because the change in time is considerably bigger than the experimental uncertainty. So there has been a change in time period when we change the mass, so the statement doesn't work. Okay. So explain briefly how you can avoid a line of sight or parallax error when measuring the length of the springs. You may draw a diagram. So let's first actually have a look at what a parallax error is. So on the left, we've got taking the measurement of length from above, so looking down on the spring. And then on the right, we've got us looking perpendicular to the scaling on the divisions. So we can see that by changing the angle of the observer, we've actually changed the reading we'd get from the measuring device by actually a significant amount. So parallax error, as it's called, can have two different effects on your results. If you take measurements without even thinking about parallax error, you'll be viewing it from all sorts of different angles, and that will introduce a random type error into your results. So that's if you don't think about it and you just take readings without giving any thought to it. If, however, you've consciously decided to take readings from a certain position, but that it's not perpendicular, that would introduce the same error every time. So it'd introduce a systematic error. But realistically, unless it's not physically possible to take measurements from perpendicular, you should be avoiding that anyway. All right, so let's go back to the original question. So the strategy is to make sure that our line of sight, those dashed lines you can see there, is perpendicular to the ruler's measuring scale, or sometimes it's often described as getting down at eye level to look at it when you're measuring using a measuring cylinder or a thermometer, for example. But that's the idea. Okay, so moving on to the second part to do with the rate of cooling of water. You're provided with a supply of hot water. Carry out the following instructions. Okay, so we've got a beaker of hot water, thermometer. So first thing we need to do is measure room temperature. So when I measured it, I got 22 degrees C. In terms of checking you've got a sensible answer and that there's not a problem with your measuring instrument, room temperature is usually somewhere between 20 and 25, depending on how many people in the room. The more people, the hotter it tends to get. Okay, so that's how we check it's sensible. Okay, so we're going to be comparing the rate of cooling with two different volumes, 150 and 250, and then we're going to record the results. Okay, so given that, let's stick in some values here. Okay, so first thing, we've got a table, so we should have units in the column headings. So that's one of the first things you'd be looking for here. And then we're told to take measurements of temperature from 0 to 150 seconds. So because the 0 has no decimal places, all of these other times don't have any decimal places either. That's the rule that I followed there. Okay, so the starting temperature, we were using a kettle, so our starting temperature should be somewhere close to the boiling point, factoring in that you've got time to take it to your actual equipment, so it's dropped to about 90. But to make sure we've controlled the experiment, we should have the same starting temperature for both experiments. And this involved me essentially with one of the experiments waiting until it had dropped to 90 before I started the experiment. So before I'm even doing this experiment, thinking about how this works, I'm expecting the biggest temperature change to be in the first 30 seconds and the smallest temperature change to be in the last 30 seconds, because the rate of heat loss is to do with the temperature difference between the water and the surroundings. So the biggest rate should be initially. So that's kind of a check we're using. Okay, so those are the things we're looking for on the table, and then you'll have got different readings going down your table depending on the different conditions you're doing the experiment in. Okay, so state whether the rate of cooling is significantly faster, slower, or about the same when using a larger volume. Justify your answer by reference to your readings. So my first problem with this question is describing a rate as faster or slower. Rates are either bigger, the same, or smaller. You can't have faster or slower rates. That doesn't make sense. But anyway, let's move past that. So the rate of temperature change for the large volume is smaller. And my evidence for that is from the data I collected. The temperature change for the smallest volume was 6 degrees over the 150 seconds, whereas the largest volume, the same time, the temperature change is 44 degrees even. So we've got a smaller temperature change, therefore we've got a smaller rate of temperature change because we've used the same period of time. Okay, so then if this experiment were to be repeated, in order to check the results, it will be important to control the conditions. Suggest two such conditions that could be controlled. So there's a few that I can think of here. We'd want the material of the beaker to be the same because that's going to be conducting heat away. We'd want the starting temperature of the water to be the same. That needs to be controlled because that could affect the results. And the room temperature as well could affect the results, so we'd need to make sure that stayed the same. One I saw quite a bit of that didn't make a lot of sense is ideally you'd want to control the surface area. So that you would actually specifically see whether it was the volume that had an effect. But if you change the volume of a liquid, you have to change the surface area. That's unavoidable because you can't compress a liquid. So that's actually not a possible control variable particularly. So there's a general rule of thumb here. So for control variables, we're looking for anything that could affect the rate of temperature change that isn't the independent variable. So that the independent variable being volume. So anything that could affect the rate of temperature change that we need to keep the same, that could be a control variable here. Okay. So just as a general rule of thumb, so once you've collected your results to see if they make sense, hopefully you'll have learned in some point in biology that the rate of energy loss to the surroundings depends on your volume to surface area ratio. And generally speaking, larger volume animals have a smaller volume to surface area ratio and therefore lose energy less quickly. So things that are designed to live in cold climates, like the seal, generally have quite a big volume, and things that live in hot climates tend to be quite small in volume, with some exceptions there is. So you can actually check whether your results agree with what they theoretically should be, and this is how I thought about that. And that finishes this video on this practical task.